Hello everyone, this is a video for topology optimization and a brief review of the paper. My name is Mingguk Jung and I'm studying in computational structure design and optimization laboratory in Yonsei University for a PhD candidate. We will briefly talk about what topology optimization is and what makes it difficult to topologically optimize the metal structures for microwave applications and how to resolve it based on the paper published in the journal Structure and Multidisciplinary Optimization. First, let's talk about structure optimization. Maybe the term optimization is familiar with you because we use this word in our everyday lives, for example, improving the efficiency of a computer code or a life pattern. However, in this video, the term optimization is somewhat different from the general term. This kind of optimization means finding an optimal solution from a set of possible candidate solutions. If applying this concept to the structural design, it is called structure optimization. Structure optimization can be classified into three categories: size optimization, shape optimization, and topology optimization. From the initial design, size optimization allows size changes such as the length of the edge, however the overall shape cannot be changed. Shape optimization allows the shape changes, however the topological properties are fixed. On the other hand, topology optimization allows the creation of holes while changing the outer shape of the structure. From now on, we will talk about topology optimization. Let's look at the compliance minimization problem for a cantilever beam that is a prime example of the topology optimization. We assume that it behaves as isotropy linear elastic material, and the given situation is the left edge is fixed while the center of the right edge is loaded. The problem is how the material is distributed in the gray region to maximize the stiffness. Can you guess? It's simple. The answer is to completely fill the gray region. Therefore, a restriction should be imposed that the amount of the material is limited to a certain ratio of the gray region. The problem can be summarized as follows. The purpose is stiffness maximization, while the system acts as isotropy linear elastic behavior, and the maximum volume is limited. In the mathematical expression, the purpose is called as the objective function. The existence of material can be represented as the value of design variable, and the other conditions are called as constraints. With this problem formulation, a cantilever beam is optimized like this. As mentioned before, the holes can be created while changing the outer shape. Then how to optimize a structure which maximizes the performance while satisfying the required constraints? Mostly, the concept of gradient is introduced. Then what is gradient? Imagine that we are going to climb up to the top of the mountain. We can schematically simplify the mountain from our view, and the control map can be created where the positions with the same altitude are connected. Regarding the top as the optimal point and the altitude as the objective value, the problem is how to arrive the optimal point from the initial point. The answer is simple. Go straight. However, different from the climb up to the mountain, and the most optimization problems, we don't know where the optimal point is and what contour map looks like. Therefore, we need the gradient. The gradient tells us the direction that the objective value changes to the maximum at that point. We can reach the next location along the gradient direction with a pseudo step size and repeat this process to arrive at the optimal point. In this case, the changeable thing is location. It is corresponded to the existence of material at each position in structure optimization. However, unlike the case of location, it is discrete. Therefore, we employ the concept of density, which has a value of 1 for a material and 0 for a void. For continuity, virtual materials which do not exist in the real world are introduced. Therefore, the material property for them must be determined. For electromagnetic problems, it is usually linearly interpolated between the material and the void according to the density value. By the way, what is the challenge in topology optimization of metallic structures for microwave applications? The important issue for numerical analysis of metallic structures in microwave range is the skin effect. It refers to the phenomenon that the electric current barely flows to a very thin depth between the outer surface of the metallic structure and a level called the skin depth. Since the scale of the skin depth is much smaller than that of the structure, it is reasonable to consider that the current cannot flow into the structure. Generally, the proper boundary conditions are applied in a form of a perfect electric conductor or impedance boundary condition. However, in topology optimization, the virtual materials are distributed along the structural boundary, so the boundary cannot be clearly determined. This is the reason why the topology optimization of metal structures for microwave applications is difficult. In the paper, the problem is resolved by combining three things: the phase field design method, new interpolation scheme, and the adaptive mesh refinement. First thing is the phase field design method. The phase field design method is similar with the density-based topology optimization method, and it takes the advantage of shape optimization by combining the reaction diffusion equations and the double wave potentials. The reaction diffusion equations are the updated scheme for design variables, which allow the topological changes. However, by introducing the double wave potentials, the design sensitivity values become 0, where the design variable value is 0 or 1. Therefore, the topological change is partially limited. Second thing is the new interpolation scheme for electrical conductivity. As I mentioned, for electromagnetic problems, the material property is usually linearly interpolated between the design material and the void for virtual materials. For example, if the design material is a dielectric material, the virtual material behaves as less dielectric material. However, in the paper, the exponential function is introduced for virtual electrical conductivity to replace the law of boundary condition for metal structures and enable the update of design variables. In the new interpolation scheme, the virtual material behaves almost the same as air. Last thing is the adaptive mesh refinement. The adaptive mesh refinement helps the law of new interpolation scheme. It refines the mesh size around the regions where the value of design variable is sharply changed, that is the structural boundary. Therefore, the effect of new interpolation scheme is maximized. Combining three things, the design process consists of two steps. The first step derives a roughly optimized shape, and it is used for the initial shape in the next step. The finally optimized shape is derived in the second step using the adaptive mesh refinement. The proposed design process can successfully resolve the problem about the topology optimization metal structures in microwave range, and the validity is confirmed through three numerical examples in the paper. Thanks for watching, and I hope you've enjoyed this video. If you have any questions, let me know by adding a comment.